Maybe just try sharing your screen for a second. It should be enabled because you're a host.
Oh yeah, good plan. Let me just find the right thing. Sorry. Oh no, it says host disabled participant screen sharing.
Okay. Let me try now.
Oh yeah, there we go. Share. What's that?
Yeah, that's good.
Cool.
So where are you joining? Are you in Cambridge? Where are you joining us from?
Yeah, Cambridge. Yeah, just my house.
Mainly at home, or?
Yeah, so some people, you know, because the advice is work at home if you can, and for some people, like I have quite a good setup, so it's very easy for me to. Some people it's a bit harder. So the office, there are a few people going into the office.
Yeah.
But yeah, I'm just at home. How's yeah, how's are you an undergraduate? Or?
Yeah, I'm doing it well. I'm in fourth year undergrad, so I'm still kind of an undergrad, but also doing a master's. So I'm like in between. Yeah, I mean it's been all right. I mean it's very strange. Just I mean although the university is still open, and so that you can still go to the libraries if you like book in slots, and a lot of the university premises are still open, but all my teaching is pretty much online, which I think for lecturers is actually better because you can just go at your own pace and divide your time as you want to. But then for tutorials, I wouldn't say it's ideal, but it's not terrible. So yeah, it's actually not been too bad. I think the main thing that I was worried about is that they didn't make people come back to university, that they didn't sort of impose the residency requirement, which would have meant that like if only half the people had come back, and I live in this huge like block of student accommodation, and this has been very empty, I think it would have been a bit sad, but like a lot of people are around and it's not too bad.
Yeah, it's because I think here you, oh no, maybe they didn't make it compulsory, I can't remember now, but yeah, it sounds kind of similar. I think maybe fourth years here do have in-person lectures, but like obviously they're online as well, so basically I mean kind of
I think it's here it's interesting because there's still a lot of in-person teaching for groups smaller than 6, and it's interesting because I think a lot of the scientists quite like online teaching, and a lot of the sort of older generation humanities tutors, from what I've heard from friends, are just very anti online teaching, and they like it sort of the traditional way, which is very like weird in a sense because they are most at risk, but a lot of them still doing online are doing in-person teaching just because that's what they're used to.
Yeah, it kind of feels like it's not going to go back entirely, right? Like,
yeah, no,
having recorded lectures is just so sensible.
Yeah, that's very sensible. I'm just gonna post in the Facebook event that I don't think anyone has joined yet. But to be fair, people
at the bottom of mine it says participants 12.
Participants 12. Okay. Then maybe we'll give it. Oh yeah, no, sorry. Yeah, I can see. Maybe we'll give it sort of three more minutes because
sure.
A lot of people tend to join a little bit late.
Sure. So are you a physicist? Or?
Yeah. I did physics and philosophy in my first 3 years, and then I decided I had enough, and I switched to just physics.
Is it? So I guess doing philosophy. Okay, not that I know anything about philosophy, but do you do the kind of more analytical side of it?
Yeah. I did. I think what put me off philosophy actually was that it involved a lot of hard math, and it was sort of more formal than a lot of the physics actually. So like a lot of the philosophy of physics I thought was very useful, but wasn't really my cup of tea and was too formal and abstract, and I didn't really enjoy it. And yeah, it was very analytical. So like I barely studied any sort of standard undergraduate philosophy. It was very tailored to science and physics.
Yeah, interesting. So do you do the same courses that like philosophy undergrads do, or is it
like some of them I could have specialized? So there's like a philosophy of physics paper which is done just by physics and philosophy, and then also done by some master students. But there's one module I did that sort of the whole undergrad body does, and the philosophy of science paper some other subjects do as well.
Okay.
But generally, it's quite like focused on doing philosophy related to physics, which is also very cool in a way.
Yeah. It's quite like, I guess there are other universities we can do dual honors, but I imagine it's a bit less like tailored that the philosophy fits so well with the physics. I don't know.
Yeah. I think it's pretty unique in Oxford. There's also just
Yeah.
a very big philosophy of physics community here.
Yeah.
Which really drives on the whole degree.
Yeah, nice.
Yeah. So I'll give it sort of 30 more seconds and then.
Yeah, sure.
We can.
Oh, we've crept up from 12 to 13.
Yeah, maybe 10 more seconds, see if any else is
No
joining.
worries.
Okay. Yeah, thanks everyone for joining us. I hope you're not sick and tired of Zoom events yet, even though it's 7th week. So today we have the pleasure of welcoming Dr. Ophelia Crawford, who's representing Riverlane, who are a company based in Cambridge who build groundbreaking software to unleash the power of quantum computers. And they're doing everything they can to get us to useful quantum computing as soon as possible. And Dr. Ophelia Crawford will give us an overview of Riverlane's workflow, their projects, their aims, and their partnerships. And she'll also showcase Riverlane's internship program, which founder of the society, Maria Villaris, had the pleasure to be a part of over the summer. And the format of the event will be a 30-minute presentation by Ophelia, followed by your questions and answers. And just a quick introduction, Ophelia did her PhD in geophysics at the University of Cambridge, and she gained expertise in numerical algorithms, and now she's developing methods to reduce the resources required to perform calculations on quantum computers. And with that, I'm just going to pass it over to you. You can share your screen, and yeah, thanks so much for taking the time and joining us.
No, not at all. Thank you very much for having me, and thank you very much for the introduction. Right. The classic Zoom question, that's all shared. Everyone can see? Yes. I'm going to assume that's yes.
Yeah.
Cool. Yeah, so thank you very much for having me. Yeah, so I'm going to talk a bit about quantum computing in general, quantum computing at Riverlane. Yeah, and just give you a bit of an example of the kinds of work we do. So yeah, I'm Ophelia. My job title is quantum scientist, which means I work on developing algorithms for quantum computers. I joined Riverlane over 2 years ago now. Yeah, I'm a physicist by background, but my PhD was in geophysics. So a very different application, although it was kind of like theoretical and computational work, so sort of overlapping transferable skills. Yeah, but it was quite a change of field for me to come and do quantum computing at Riverlane. So yeah, about Riverlane, we are based in Cambridge. And so when I joined the company, for most of that first year, it was just 4 of us. But since then, well, the picture on the right, you can tell, has not been taken recently because we're all sitting almost now, makes me cringe at how close we're sitting. It's a bit of a shock to see. So that's about a year ago, we were 12 people, and now we're 24. And the technical team there is about 18 from a really broad range of backgrounds. So yeah, physicists, some like quite a range across the physicists in terms of how much quantum experience before, chemists, mathematicians, computer scientists, kind of computer engineer side of things. And yeah, very broadly what we do is, so we don't build quantum computers, but otherwise we cover kind of a lot of the stack above that. So developing the software for the quantum computers and trying to bring close to the present day the time when they can do useful calculations. And so for us, this building of software is divided into kind of two camps. So we have a product that's called Deltaflow, and this is broadly an operating system for quantum computers, and I'll talk a little bit more about that later. And also what we call Anion, which is the team I'm more part of, so thinking about developing applications for quantum computers, and in particular, computational chemistry type calculations. And again, I'll talk a bit more about that later. So I just wanted to begin with a bit of an introduction to quantum computers and how they work. I appreciate a number of you may already be very familiar with this kind of stuff, but it just gets us all kind of onto the same page. And when I'm talking about quantum computers here, I'm thinking about what's known as gate-based quantum computers. So you may have heard of other types of quantum computers, something like, so there's such thing as quantum annealers. You may have heard of a company called D-Wave who built those types of quantum computers, but they're not. So yeah, I'm not thinking about that type of quantum computer here, and that's not something we focus on. So yeah, we focus on gate-based quantum computers, and they're kind of the sort of three important aspects are, and I'm just going to outline them briefly, is so what the states are on the quantum computer, how we manipulate those states, and then having manipulated them, how we make measurements on them to learn something useful. So to begin with, thinking about states on quantum computers. So you may well be familiar with on a classical computer, or I'm just going to see if I can get a slightly bigger mouse. Oh, that's maybe a bit better. So on a classical computer, data is stored in bits, and each bit can have a value of 0 or 1. On the quantum computer, the imaginatively named equivalent is a qubit. And the key is that the states can be in some combination of 0 and 1. So here I've written this as alpha times 0 plus beta times 1. So this sort of straight line and angular bracket is known as a cat. If you've seen it before, great. If you haven't, don't worry. It's just a way of writing a quantum state. And we could also represent, it's also sometimes useful to have another notation of way of writing these states in a vector. So this 1 qubit state could be represented as a vector of the coefficients alpha and beta. So going up to 2 bits on the classical computer, each of them can either be a 0 or a 1, and so you get one of the 4 states. On the quantum computer with 2 qubits, it can be in a combination, any combination of those 4 states. And again, we could write that state as a vector of length 4 with the alpha, beta, gamma, delta coefficients. And so taking this all the way up to n bits, on the classical computer, each one of them can be a 0 or a 1. And so the classical computer exists in one of the 2 to the n states. Whereas on the quantum computer, it exists in some combination of all of the 2 to the n states. And so the general sort of possible state spanned by, oh, I've just realized that says bits there. That meant qubits. The general state could be captured in a very big vector of all 2 to the n coefficients. So it would take a lot of space on a classical computer. It would take a vector of size 2 to the n to store a state that only needs n qubits on the quantum computer. So now we have our states. We'd like to be able to do things to them, manipulate them, perform calculations on them. And on a gate-based quantum computer, we do that through what are known as gates. And these are basically operations on the qubits. So there are 2 main types of gates that we tend to think about. 1 qubit gates, which, as you might guess, act on 1 qubit. 2 qubit gates act on 2 qubits. So an example of a 1 qubit gate is shown here. We start with the qubit just in the 0 state. We act this particular 1 qubit gate here on it, and we end up with some combination of the 0 and the 1 state on this qubit. And again, we can represent that action, that manipulation of the qubit in terms of matrices and vectors. So this is the matrix of the gate, this is our initial state, and then we end up with our final state with the cosine sine coefficients. And we can apply these 1-qubit gates to any qubits, but in general, application of those won't give us the most general quantum state. So we'll always just end up with a quantum state that's a product of that you can split into individual terms on the individual qubits. So the state on the first qubit, the state on the second qubit, etc. But that isn't the most general quantum state. So what we also need are 2-qubit gates that act on 2 qubits. So one example is the controlled NOT gate. And this takes 2 qubits as its input. It flips the number on the second qubit if and only if the first qubit is equal to a 1. So C0 acting on 0, 0, the first qubit's a 0, so it does nothing. C0 acting on 1, 0, the first qubit's a 1, so it flips the second qubit, which gives us this state here, which you can see we can't split into a product of a state on qubit 1 and a state on qubit 2, like we had here. And so this combination of 1 and 2 qubit gates allows us to prepare kind of the full possible space of quantum states. So now we have our states, we can manipulate them. But in order to do something useful, we also need to make measurements of these states, having done the manipulation we want to do. So making measurements on quantum computers, you may know this from quantum mechanics, but if you do, just to remind you, or if you don't, to try and outline, when you measure an operator on a quantum state, what you do is project from that quantum state into one of the eigenstates of the operator. And having done that, the measurement you obtain is the corresponding eigenvalue. So I will give an example of that in a slide, which will hopefully make that a bit clearer. On the quantum computer, we can't measure any old operator we like. There are sort of set ones that we're enabled to measure, and these are what are known as Pauli operators. So these can be represented, the 1-qubit Pauli operators, by these matrices on the right. So just to take this Z Pauli matrix as an example, we can see that its eigenstates are just the 1, 0 vector with eigenvalue 1. And remember, we have this notation in vectors where 1, 0 represents the 0 quantum state. And then the other eigenvector is 0, 1, which is the 1 quantum state, and that has an eigenvalue of -1. So when we make a measurement of Z, we will project into either this state and measure a 1, or this state and measure a -1. And the probability with which we make those measurements is given by the amplitude squared of the eigenstate in the quantum state. So if we have the quantum state alpha beta, we'll measure a 1 with probability modulus alpha squared, and a -1 with probability modulus beta squared. If we keep making measurements and take the average, we'll obtain what's called the expectation of Z. So this is like the expected value of the Z operator on the particular quantum state. And we can see here that that's equal to modulus of alpha squared minus the modulus of beta squared. And we'll talk a bit more about kind of how you then make use of these expectations of Pauli's later when I come to thinking about computational chemistry applications. Oh yeah, so then everything we've talked about so far, I've just talked about Pauli's on 1 qubit, but you can then just measure different Pauli's on different qubits. So this here is representing a quantum circuit with qubit 1 and qubit 2 represented by the straight lines, and then the blocks represent gates acting on the qubits. So we might act some circuit on the qubits to prepare a particular state, and then at the end we decide to measure X on qubit 1 and Y on qubit 2, and then we can take the product of those measurements to get a measurement of the operator that's the product of the two. So those are kind of the fundamental things that gate-based quantum computers need to be able to do. There are quite a lot of different ways of realizing those quantum computers, different technologies you can use. I think this 6 kind of captures most of them. The most common 2 are the top 2, so superconducting quantum computers and trapped ion quantum computers. So for example, Google has a superconducting quantum computer, IBM has a superconducting one. There are actually also quite a number of UK hardware providers. So as an example, and yeah, ignore the weird kind of color shading here, but this is showing the laboratory of Oxford Quantum Circuits. So this is you may have come across, this is a company based in Oxford. They span out of the physics department, who are building a superconducting quantum computer. And this
quick interjection. Sorry, we have the pleasure to welcome someone from Oxford Quantum Circuits on Monday. So if you want to learn about quantum hardware, then the next Monday you can tune in to Dr. Jonathan Burnett, who's the head of hardware at Oxford Quantum Circuits. Sorry.
There we go.
Continue.
Good timing. Well, here is a sneak peek of their device then. Yeah, I don't know anything about, or next to nothing about, how actual quantum computers work. So yeah, I'm sure there will be lots to learn from him next Monday. Yeah, and just to say, so you may well know, whilst these quantum computers do exist, and people like Google have sort of tens of qubits, they're not yet big enough to do you know, big useful calculations, but they are getting better as time goes on. So this figure here is showing kind of how the capabilities of different technologies have improved over time. So you can see quite a nice, almost Moore's law of the improvement on the quantum computer. We've got this logarithmic scale here, and so it's kind of increasing exponentially. So we made this plot a few years ago. What's interesting is we were kind of predicting that the capabilities would be good enough to do a calculation called quantum computational supremacy in about 2019. And you may have heard about a year ago, Google did achieve this milestone. So this was the first time a calculation had been performed on a quantum computer that couldn't be performed on a classical computer, with the caveat that this calculation was deliberately designed to be good for the quantum computer and bad for the classical computer. And it's not really a useful calculation, but you know, it's a very important milestone onto where we're hopefully going, which is quantum computers getting better and better, so that one day they are able to perform calculations that classical computers can't, that are useful. So having, given a quick introduction to quantum computing as a whole, I'm just going to talk a bit more about the kinds of things we do at Riverlane. So I mentioned we have these 2 main products. So one, which is called DeltaFlow, is it's kind of an operating system for quantum computers, and it's quite different to an operating system on your desktop computer, as you might imagine, but the idea is so quantum computers have lots of different components required for them to work. So at the very bottom, there are the qubits, but then there are also different control parts to, apply the gates and manipulate the qubits. And we typically also want a classical computer alongside to do some of the calculation too. So there are quite a lot of different bits to integrate. And in order to kind of optimize the performance of your device, you need to think quite cleverly about which calculations you want to do where. And so this is the idea behind DeltaFlow. And as part of that project, we have a grant with lots of the UK hardware providers, so including Oxford Quantum Circuits. There's also another company in Oxford called Oxford Ionics, which they're building an ion trap quantum computer, and some other UK hardware providers too. And if you want to know, if you would be interested in learning more about Delta Flow, there's actually a YouTube video that, so Maria, who, I think was one of the founders of this society, she was one of our interns last summer, particularly working on kind of outreach and developing educational materials. So yeah, she's put together a YouTube video. If you search that YouTube or go to the Riverlane YouTube channel, you can find that if you're interested. Oh, and that's just to say, this is why this picture has colors on, is it matches up to the different parts of the stack here. So you can see kind of the different bits at work in the lab. So the other side of what we do is, applications, and the particular application we think about is broadly computational chemistry. So when I'm talking about computational chemistry calculations, we're thinking about learning about properties of molecular or solid state systems. And in particular, in order to do that, you need to understand the ground state electron configuration of the system. And from there, you can measure the ground state energy and you can measure other properties. So as a simple example here, I have a highly schematic representation of a water molecule. And then this plot on the right-hand side is showing the ground state energy as a function of the bond length between the oxygen and the hydrogen. So I'm assuming the bond angle is fixed at the optimal value, and then we're varying this bond length along the x-axis. And on the y-axis, recording the ground state energy for that particular geometry. And so each kind of dot here would could be done through a separate chemistry calculation. And then we build up this picture of the energy surface, and we can see where the sort of stable geometry is. The molecule will naturally come down to the lowest energy at about 1 angstrom. So I said what we're interested in is ground state electron configurations. So yeah, learning how the electrons are distributed in the molecule. And typically the way we think about the possible electron configurations is through what are known as molecular orbitals. So very schematically, each green line in this plot represents a molecular orbital, which is a possible location of an electron in increasing energy going up the plot. And each molecular orbital can have 2 electrons in, one spin up, one spin down, represented by the orange up and down arrows. So water has 10 electrons, and we might guess, okay, the lowest energy electron configuration would just be fill up the molecular orbitals from lowest energy to highest energy. And this gives us a pretty good approximation of the true ground state energy. But it isn't actually the ground state electron configuration because of the interaction between the electrons. So yeah, because of this interaction, actually no single distribution of electrons in the molecular orbitals is the ground state. It's in general some superposition of electron configurations. And you're possibly, from me using that word, kind of seeing a connection to why it's useful to do computational chemistry calculations on a quantum computer. So this system's quite small. We could quite easily write down all the different ways the electrons can be and write them as a sum and kind of optimize over the system to find out the coefficients. But in general, as the system gets larger and larger and larger, the number of states we need to consider gets bigger and bigger and bigger, and we can no longer capture all of them on the classical computer. But because the quantum computer can prepare this superposition of states quite naturally, it potentially offers a way to do these calculations when a classical computer can't. So one particular method for performing these chemistry calculations is what's known as the variational quantum eigensolver. So I've said we want to find the ground state energy of a molecular system, and this corresponds to finding the lowest eigenvalue of the Hamiltonian operator associated with the system. And the way the variational quantum eigensolver, VQE, works is it searches over some parameterized space of quantum states that's known as the ansatz to find the one that has the lowest expectation of the Hamiltonian on the state. So if you could search over all possible quantum states, you would definitely, and you found the minimum, that minimum would be the true ground state. So you hope, searching over the whole space is too big, so you have to limit it somehow, but you hope you can do that in a sensible way and still find something that's a good approximation of the ground state. So the way the algorithm approximately works is you choose some initial values of the parameters, you on the quantum computer prepare the quantum state that corresponds to those parameters, make some measurements of it. And you'll remember that when we make a measurement on a quantum state, we project it into an eigenstate of that operator. So we can no longer, we've lost the original quantum state we had. So if we want to do another measurement, we have to prepare the state again and then make another measurement. So this here loops back and forth, preparing the state, making a measurement. Eventually, we've got enough measurements that we can get the expectation of the Hamiltonian on the state. And we keep doing this for new parameters until we think we found the overall minimum. And it's hoped that this gives us a good estimate of our ground state energy. I'm going to tell you a little bit more about some of the work we did about a year ago on looking to reduce the resources required to do a particular part of this process. So that is kind of what measurements we make on the quantum state and then how we evaluate the expectation. So you'll remember I said the only operators we can measure on the quantum computer are Pauli operators. So we can't measure our Hamiltonian directly. We have to write the Hamiltonian as some sum over coefficients and then also the Pauli operators. And then in order to get the overall expectation of the Hamiltonian on the quantum state, we measure, we make lots of measurements of each of the Paulis in order to get an expectation and then multiply by the coefficients. So yeah, if one of the Paulis we wanted to measure were x1, y2, we'd make lots and lots of measurements of that Pauli in order to get the expectation before moving on to the next Pauli. So something I mentioned on the last slide was that obviously when we make a measurement, we project into the eigenstate of the operator. And so in order to make another measurement, we need to prepare the state again. However, you might know from quantum mechanics that operators that commute actually share eigenstates. And so what that means is we are able to obtain measurements of Pauli operators that commute simultaneously, or quantum mechanically, we know that we are. And so one way to reduce the resources required to get an expectation of the Hamiltonian is to, so say this schematic here, if our Hamiltonian is a sum over 16 Pauli operators, and say we could split those Pauli operators into two sets of commuting Pauli operators, instead of having to run 16 circuits, we'd only have to run 2 circuits to get a measurement of all the Pauli operators. Yeah, and so we worked on, we did some work on this method, and in particular thinking about 2 questions. So in general, there'll be lots of different ways you can group the operators, the Pauli operators, into commuting groups, and so you'd like to do that as optimally as possible. And so we thought about that method. And then also you need a way of actually obtaining measurements of all these Paulis. So in general here, you can see if I've measured x1 and y2 on the 2 qubits, even if, so say the operator z1, z2 would commute with that operator, but there's no way of measuring it because we've already measured x and y. And so in general, you need to add a bit of circuits at the end in order to enable you to get the measurements you want. And so we also worked on methods of constructing those circuits. And just to show you some of the results, so this is showing for systems of different size. Yeah, we're thinking about chemistry calculations here. So for different molecules, looking at the speed up our method offered. So kind of the factor reduction, the number of measurements you need over just doing traditional VQE where you measure each Pauli individually. Yeah, so that's sort of a whistle-stop tour of some of the work we've done at Riverlane. And so I just wanted to tell you a little bit about potential opportunities that we will have coming up. So there are two main things that I think will be relevant so I don't have exact timelines on the quantum scientist full-time role. Hopefully sometime in the spring, we might be hiring for those full-time positions. So that would be a role like mine. So kind of on the algorithms side of things. And yeah, one thing I should say there is my background is obviously not in quantum computing at all, and we don't necessarily expect people to have that background. Kind of the main thing we're looking for is just, technical ability, problem solving ability, and that kind of thing. So yeah, one thing I should say is we do typically ask applicants for the full-time role to have a PhD. But yeah, if that fits you, please do look out for that role next year. So the other thing that I can give you slightly more detailed timelines on is our summer internship scheme. So this year, we're running one scheme for third year plus undergrads, master's students, and PhD students. Again, we don't expect you to have extensive quantum computing knowledge or anything like that. The idea would just be, kind of a typical summer internship. You'd come and work for us for 10 to 12 weeks. Ideally, it would be, well, assuming the world can do that, it would be in our office in Cambridge. But this summer we did mix, remote and office working as worked. And typically our interns, you get allocated a supervisor in your own project, but also we are very collaborative. So it would very much be kind of being part of the technical team. And yeah, applications for that open in January. So if that sounds interesting, please do keep an eye out for that. And there are just a couple of blog posts that might be interesting, relevant to that. So a couple to do with our past interns experiences. So one from 2 summers ago, one from last summer. And there's also a blog post with some, that we wrote just after our applications round earlier this year, just with, some tips there. So that's, all from me. I'm very happy to take questions on, anything. I've kind of, anything and everything.
Yeah, thank you so much. So if you have any questions, I think it's easiest if you post them in the Q&A section, but I see there's a question in the chat. So Hamza, if you want to, I can allow you to speak and you can ask it yourself. Maybe that's...
Hello.
Yeah.
Hi, Ophelia. Thank you very much for that talk. This is one of the few quantum computing talks I've come to, and the industry looks really, really interesting. My question was just simply, I'm a second year, and I think you mentioned third year undergrads only for the internship. Is that a strict thing, or is it just more of a guiding rule?
Yeah, unfortunately, we are quite strict on it. Just we do get quite a lot of applicants, and kind of last year we had sort of 200 for 6 places. So
okay.
It's just in terms of kind of now, it's a way of narrowing things down for us, and so we are unfortunately quite strict on that. But please do apply in another year.
Yeah, thank you. Anyway, cheers.
Yeah. Any other questions? Otherwise, yeah, thanks so much for the talk. It's very interesting. So yeah, my question would be is that obviously you're working on the sort of more algorithm side and optimizing the use of quantum software for solving problems in quantum chemistry. But I recently came across a paper that was, I think, a little bit pessimistic in terms of the outlook of how useful quantum computing would be in solving problems in quantum chemistry. And if I remember correctly, the paper just said that if we take into account something known as parity superselection, then actually most of the correlation between orbitals is classical, not quantum. So my question goes more into the direction of, do you have people sort of working in an explorative role, looking for which problems actually will lend themselves to being solved with quantum computers, or where quantum computing could be particularly useful?
Yeah, absolutely. Yeah, that's a really good point. It is still, yeah, it is still kind of unknown exactly where quantum computers will offer the most, yeah, the best advantage. Yeah, you're absolutely right, and that is a big part of what we think about is, okay, yeah, what problems will be the most interesting and the most useful ones. Yeah, definitely.
So is that just basically at the forefront of everyone's mind in thinking about which problems are the sort of the most pressing and which lend themselves best to being solved with quantum computers?
Yeah, definitely. I mean, I think that's that is a really big question, is what will be the first useful calculation a quantum computer does. Yeah, it's definitely an unknown and definitely an important question. Yeah.
Great. Yeah, then there's another question in the chat. I don't know if Alexei, you can, I'll give you permission to speak if you want to. Maybe he's not unable to speak. Alexei's question is, when you were talking about the circuit optimization, isn't it a hard problem which requires a quantum computer itself?
So the particular bits I was talking about there was, yeah, so how to enable measurement of multiple commuting Paulis. And yeah, in terms of, so the way we went about it, yeah, there is a paper if you're interested in reading the actual details, but I'll try to explain it. So we kind of tried to, by construction, use as few gates as possible, but there isn't necessarily a guarantee that it's the fewest gates you could ever possibly need. In terms of needing a quantum computer for circuit optimization, I think maybe what you're thinking, I think my understanding is, so when we're building a quantum circuit, we have these distinct gates. There are only a finite number of things we can ever do, but it very quickly becomes a very large number of different gates we can apply in different orders in different places. And one of the things, so it's a kind of a combinatorial optimization problem. You want to find a particular one of these layouts that does the thing you want in using as few quantum resources as possible. And one of the possible things people consider using quantum computers for, although the advantage is like not necessarily clear, is doing that kind of combinatorial optimization problem. Yeah, so I guess I would say in the context we were thinking about it, we try to, by construction, get an moderately efficient way of doing it, but yeah, it isn't necessarily the absolute most efficient way.
Yeah, if no one else has any questions, I have another question, which is it's maybe very difficult for someone working in quantum software, but obviously quantum software will only take us so far if we don't make significant advances in hardware. So I was wondering, what if you had to guess, or if, say, your colleagues at Riverlane had to make a bet as to which quantum hardware technology is the most promising, where would you put your money on? Would it be ion traps, semiconducting, photonics, superconducting?
I'm going to be quite boring, and I'm afraid I'm not going to pick one. So they do have different, different advantages and disadvantages. I would say, I mean, I'm going to give a diplomatic answer, certainly. I also honestly, I don't know enough to make a strong stab. But yeah, they definitely do have different advantages and disadvantages. Part of what we're trying to do is, so developing the applications, it kind of doesn't matter when you're thinking about things in terms of gates that could be implemented on sort of whichever device you want. And then part of DeltaFlow's role is to really take into account the specifics of a particular device in order to make it as good for that particular device. So I'm afraid I'm giving a very boring answer, and honestly, I don't know. And yeah, I guess we are trying to cover the whole space. Yeah, sorry for that boring answer.
Oh no, that's fine. Are there any other questions? Feel free to post in the Q&A or post in the chat. There's also a flyer I have, which outlines sort of I think the internship opportunities at Riverlane, but unfortunately sharing files is disabled in the webinar, but I can post that in the Facebook event if anyone's interested.
So that also, we have actually slightly changed our internships, I think, since that flyer went out. As it is there, it's kind of split the undergrad and PhD internships in two. So yeah, in fact, those sort of general ones where we don't require a quantum computing background have kind of been, have sort of been merged into a single summer internship scheme. But yeah, but broadly, like the requirements will be the same, and I think that the dates will all be the same. So yeah.
Yeah, I mean, I guess if there's, well, there's another question. Oh yeah, there's another question. So yeah, what level of quantum do successful applicants usually have? I'm guessing, yeah, that's probably for the internship scheme, or maybe for the quantum scientists as well.
Yeah, so for the internship scheme, we absolutely don't require extensive knowledge. That said, because we do have a lot of applicants, if you're able to demonstrate that you have an interest in the field, that is useful. Kind of similarly for the full-time roles, my background, like I was an undergraduate physicist. I think I had done, one quantum information course, but otherwise, I did not know anything about quantum computing. And there, I think we are much more looking for, general ability, and physics and maths or the relevant subject capabilities, but it's not really an advantage if you happen to have learned some facts about quantum computing. It's more having the general ability, and if with that being able to show, oh, you are genuinely interested in quantum computing, that is useful too.
Yeah, great. Yeah, fire away with any more. Okay, there's another question. So Tim, I'll give you permission to speak if you want to ask your question.
Yeah, hi, can you hear?
Yep.
My question is, does Riverlane deal with other parts of quantum computing? Like, for example, quantum machine learning or just quantum chemistry?
Yeah, so quantum chemistry is the application we're mainly focused on. Yeah.
Right.
Yeah.
Great. Yeah, far away with any more questions to everyone who's still here. But I guess if there's no more questions, thank you so much, Ophelia, for taking the time and joining us.
No, not at all. Thanks very much for having me.
And hopefully this has been useful to all our listeners as well who are interested in quantum computing and maybe will apply to either the internships or the position as a quantum scientist. So yeah, I hope this was useful for all of our listeners, and I'll post the flyer in the Facebook event. But you're probably better off just checking Riverlane's website, which will have the most up-to-date information.
Yeah, also please do feel free to email me. I've closed my presentation, but my email addresses are on the website. So if you'd like to email me to ask a question, please do feel free.
We have another, yeah, no more questions, just a thank you.
Great.
Thanks again for everyone who tuned in, and thanks Ophelia, and yeah, have a great day. And yeah, on Monday we're hosting Oxford Quantum Circuits. We'll post about that very shortly because we only confirmed that event today. But yeah, maybe if you're interested in quantum hardware, you can come along then as well. Bye everyone.